Bodipan, and we will discuss the clinical chemistry. But first, we will start about the our lecture, which is the fifth lecture, and we will discuss some topics that is related to that. So the key concepts we have to know. Some concepts we have to know it. The first one is blanking, and what we exactly blanking? There is something is called blocking that we have used it in the Western blotting, and actually we use the blocking by what we called it is the bovine serum albumin, or we can say free fat milk. We can use the casein. All they are used for the blocking. But there is something is called blanking, and the blanking is to correct the background color in the endpoint reaction. When I said endpoint reaction, it means that this reaction that is like we just watch the transformations from the substrate to the product. That's mean exactly with the end point reaction, like we measure the product of this reaction. Okay, so that's exactly what is the endpoint reaction. But actually I'm not talking now about the endpoint reaction. I'm talking about what is blanking. Blanking is like correct the background noise, color, etc. that is present in the endpoint reaction, because I want the clear results. Some they said is to remove the background noise or interference in the measurement. Exactly what we can say, it's interference things. And the applications of blanking: spectroscopy by absorption. Some they are used titration to account any impurities or reagent in the sample. Chromatography, like also high performance liquid chromatography, we actually use it also sometimes to clear the interference thing. So when I said blanking is to clear the background noise, to anything that is can maybe interfere with the measurements of the analyte or something that I want really to measure it. So I don't want anything that is interference with it, so we can say it's a blanking again. And for the final time, blanking is to correct the background noise. I can say it's about the color, it's about maybe the interference or anything. It's not about the color. Okay, time window used in the rate reaction. So there is a difference between the endpoint reaction and the rate reaction. Actually, the rate reaction, it's really helpful in the case of measurement the activity of the enzyme, because I'm not just concerned about the project, but I'm just focused on how this enzyme, how this enzyme activity. So the time window that is used, we can say it's a time window here. So we use it in the case of the rate reaction to optimize the measurement of the target analyte. Like we use like time, like certain period of time just to measure these rate reactions. So we have two concepts until now. We have a blanking to correct the background noise in the endpoint reaction, and we use the time window, and that is used in the rate reaction to optimize the measurement of the target analyte. Common approaches to select for the analyte, like if you want to select analyte, actually we use many approaches. The first one is the enzyme assays, and we can use immunoassays, and we can use also ion selective electrodes. But it's not about endpoint reactions or rate reactions. It's actually how to select the analyte. So sometimes we use enzyme assays, we sometimes use immunoassays, we use ion selective electrodes. I can say like they are the target. Pre-analytic separation techniques can be used to isolate the analyte from the interfering compounds, because it's so important, like we do the blanking, That is exactly the blanking. So we use something is called the pre-analytic separation techniques. We use some techniques to separate the analyte from the interfering compounds, and actually we use it as a pre-analytic, and that's for sure is called pre-analytic. So here show us how is the blanking. Here we have the absorbance, and here we have the time. It's always the time is in the horizontal view and the absorbance is in the vertical. So we have here the time of the initial reading. This is the time of the initial reading, and this is the time of the final reading. And we can say this is the blank zone. Okay, so here is the sample added, and then the blank zone that we just add reactive reagent is added in this time. Why we do that? Because we want to block anything that is not related to the analyte, so we can say it's a blanking, and then this is the final absorbance, so we can measure our analyte correctly. So what is the blanking? If we want to use it as equation, endpoint signal minus signal period to the addition of the reactive agents. So we can say that the reactive agents that is to do the blanking, and we want to know what we do actually. What is the blanking that is can be done? We look at the product or the signal, like we see the result signal and minus it from the signal that is was superior to the addition of the reactive analyte, and that's exactly what is the blanking. So what is the blanking? Blanking is endpoint signal minus signal that is superior to the addition of the reactive reagents. So we have here the reabsorbance, and we have here what we called it as the time, and here the sample is added, and then the active reagent is added. So reaction interfering substances here, so, and then the reaction target analyte, and here we measure here the like here we measure the reaction target and the analyte, but I can say here is a blanking because it will be happen after the addition of analyte, so it will be clear, and then we make another measure when the target and the analyte with each other. Rate and endpoint reactions. So if we talk about the glucose, we have the glucose NADP positive hexokinase, that's hexokinase, like take this phosphatic group and add it to the glucose. That's actually what is happened. And you know that the hexokinase, the calcifications of this enzyme is 2. Why it's 2? Because it transfer the phosphatic group from the NADP and add it to the glucose to be glucone 1,5 lactone, and plus NADPH plus H positive. We can measure it as the endpoint by the maximum amount of the NADPH here, and we can also ensure it is as a rate reaction by the rate of the NADPH is 4. You just said that the reaction can be acted by both by endpoint reaction and the rate reaction. And the question is why? Because we have the glucose, we have NADP positive, and we add the enzyme which is called hexokinase to be like glucone 1,5 lactone plus NADP H plus H. So we measure how the amount of the NADPH, we can measure the endpoint reaction, and the same we can measure the rate reaction at the same time. Then we go to something which is called enzymes. Enzymes are used as we have like defined before what is the enzymes, and we said that the enzymes are biocatalysts, yeah, because it speeds up the chemical reactions. And here we have another definitions for the enzymes. We can use them as the analytic reagents. of measurement of the cerebral metabolites and substrates. Like we use these reagents, we use these enzymes as the reagent to analyze the substrates and the products and the metabolites. We use them as a measurements, and we can use them as immunoassay to detect and the quality of the immunological reaction. So the enzymes, it's not about that they are as just catalyst. We can use it as another things, like we use it as analytic reagents, like they are used for the measurement of the cerebral substrates and the metabolite. We can use them as the immunoassay because we can detect all the immunoreactions. So the enzymatic assessment of the enzymes, for examples, A is substrate, B is substrate also, but we use the enzyme, so that is lead to the addition of C and D. So we can measure the enzymatic, what we can assess the enzyme A. And in the example, like here is the enzymatic assessment of A, that's mean its substrate concentration, and sometimes we just assessment of the enzyme. Here we have the transferrin, okay, and this transferrin is soluble because it's present in our blood. Then it come antibodies, and these antibodies, they just bind to the transferrin, and what they form immunoprecipitations of a transferrin antibody complex. So that is lead to the transferrin antibody complex, and after the transferrin antibody complex, they are just make this complex, then they are become insoluble. So we have a transferrin, we have also antibodies, and when they are just bind to each other, make complex which make them insoluble. And then I will talk about another things, like these chapters is full of things that they are not related to each other, I can say sadly that. So we have a Abytinia and we have a Bitia, and we want to understand what is the difference between them. So the first one is P, that's mean particle, E enhanced, T turbometric, and I don't know what is referred for what, and then I immunoassay, but it's called Bithynia. That is the name. I have no idea why there is N here, but it's called Bithynia, and that is mean particle, enhanced, turbometric, immunoassay. Okay, so measure cloudness or turbidity from the immune complex. As we see here, we have a transferrin bind to this antibody, then it make the complex, and this complex is insoluble. So if this complex insoluble, then makes the turbidity because they are scatter the light. Okay, so we measure the cloudness. When I said measure the cloudness, because they are scatter the light, so we can say that that's exactly what is the Bithynia. If you just remember what is this abbreviation referred to, then you understand what is about. So it's a particle enhanced turbometric immunoassay. So it measures the cloudness, or we can say turbidity, of the immune complexes. So what is causes light scattering? Because it's turbidity, so light is scattering, and it's used for the larger molecules of proteins. So in increasing the turbidity, that's mean in increasing the concentration. So we have something is called Bithynia. Okay, and the question is, what is the Bithynia? Is a particle enhanced turbometry immunoassay. And when I say turbidity, that means we measure the cloudness of these products. We measure the turbidity of these particles, and these, I mean here in the particles is immune complex. When I say turbidity, that means they are causes scattering of the light. And most particles, they are large particles. When they just form immune complexes that they are large enough, then that is causes scattering the light. And once the turbidity is more, that means the concentration is more also. So concentration increase, that's mean I mean here when the turbidity increase, that's mean the concentration it will be also increase. And then we have a Bitia, okay, and that is mean exactly particle enhanced, but T is a transmission amino acid. So they have the same thing, but here particle enhanced turbidity immunoassay here is called particle enhanced transmission immunoassay. That's we add in because we want just to distinguish between them. Okay, when we add in that's mean it's turbidity. Okay, so BTM, it measures the decrease in the light transmission because we measure the light transmission, not the light turbidity. And when there is a decrease, that means that there is absorbance, and that is used for the smaller molecules. If there is decrease the transmission, exactly that's meaning increase the concentration. Because if you just understand what is the idea behind this, you can understand why is when decrease the transmission it indicates more concentration. Because we have here the particle and there is light transmission through it. If this particle, we said that is measured the light transmission, but actually it measures how the light absorbs. This particle absorb the light or maybe just hit this light, and then the amount of the light will be decreased once these particles are absorbed or larger enough, or the concentrations it will be more. So we can understand that the turbidity by the large molecules transmissions for the small molecules. And now we want to understand what is the offline treatment and what is the online treatment. So the offline treatment, what we can do is we just mixing the serum with the polyethylene glycol. Okay, so mixing the, here we will talk about this offline and then we just describe here in it. Okay, describe the drawing here. So we give the serum, we just bring the serum, okay, and then mix it with the polyethylene glycol. Then the polyethylene glycol reacts with everything, with every particle that is present in this sample except the high density lipoproteins. It doesn't react with the high density lipoproteins. It reacts with everything else than high density lipoproteins. Why we call it offline? Because it does manually and not automatically on the analyzers. Precipitate from the low density lipoproteins, very low density particles, the participate forced to the bottom by centrifugation. So that is can be happen by the centrifugation, and then leaves clear solution of the high density lipoproteins. So this clear solution of high density lipoproteins cholesterol treat with the cholesterol esterase that is produced, a product that is can be measured by the photometry. Let's go to the picture, go to the drawing and understand how is that can be happen. So we have this sample to understand what is the offline treatment. So we have here this sample. As you can see here, this is the sample. And we have high density lipoproteins, low density lipoproteins, very low density lipoproteins, and then we add something is called polyethylene glycerol. That's it. We add polyethylene glycerol, and I said that the polyethylene glycerol react with every particles except the yellow one, which is the high density lipoprotein. So all these particles, what is happen? They are just go to the bottom, because it's react with everything. Okay, so there will be precipitations. The question is just I put the sample high density lipoproteins, low density lipoproteins, very low density lipoproteins, but they are just mixed up. Okay, they are just mixing with each other. That's why I put the polyethylene glycol, because it binds to everything except high density. It binds to the low density lipoproteins, binds or reacts with the very low density lipoproteins, but the high density lipoproteins no. So all these particles, they will be precipitate. I can say it's precipitate, yeah, but by centrifugation that helps it's better. So all very low density lipoproteins, very low density lipoproteins, they will be precipitate under in the bottom of this sample, and above this sample it will be the high density lipoproteins. So the participate forced by the bottom by centrifugation. And we said before how the centrifugation happened. We just collect the sample for 30 minutes, and then we just put this sample inside the centrifugation or centrifuger for 15 minutes in the 5000 the speed of it. Okay, so it will be happen the precipitations of the low density lipoproteins, very low density lipoproteins, and then the high density lipoproteins it will be about. Then what we can do, treat it. That's why I said treatment, because it will be treated by the choline esterase. Why we do the choline esterase? The choline esterase act on the high density lipoproteins and give the product that this can give to us, that we can measure by the photometry. If the high density lipoproteins we can measure it by the photometry, then we can use directly the photometry, but actually we use the choline esterase enzyme. Okay, why it's called offline? Because it done manually. Okay, and then we automatically put it in the analyzer. Then I'm talking about the online treatment. There will be two steps. Introduce the reagents cholesterol oxidase that destroy the non-high density lipoproteins cholesterol that is not bound to the lipoprotein, and then the only one that is present in the sample, high density lipoproteins. Then we get the choline esterase enzyme, or no, it's cholesterol esterase enzyme, because it will be lead to the production of the product that we can measure it by the photometry. So here we didn't put the polyethylene glycol that make a reaction or this stuff. No, we just put the cholesterol oxidase, and the cholesterol oxidase destroy everything except the high density lipoproteins. So it will be all the high density lipoproteins. Then we put something is called cholesterol esterase enzyme, and after we put the cholesterol esterase enzyme, then that is lead to production of the, or that is lead to the production that is can we measure it by the photometry, and that's what we call them online treatment. So by this we finish the fifth lecture, which is really small and help you understand anything. I like that is mix of many things, but it's important to know it. And thank you. And you have just to know that is T here is turbidity, and here T is transmissions, and remember N that's mean turbidity, and it's important for the large molecules. So thank you so much, and the upcoming lecture it will be about the potentiometry, and it will be very very large lecture of the upcoming lecture. So thank you so much for listening.